So first thing is, what would be r equals to 5? What would this do? So regardless of your array, you're always plotting 5, right? So it's going to be circle of radius 5. How about theta equals to 30 degrees? What would this do? In this case, yeah, it would be a straight line, right? Yeah. What kind of line would it be?
30-degree line.
All the lines that it will be a 30 degree. This looks more like 45. This 30 degree line, because every point on this line has the property that the angle is 30 degrees. Okay? So it's going to be a straight line. Another thing that's interesting is, what if you have r equal to theta? What would it be? When theta is 0, it's 0. When theta, yeah, it'll be like that, right? And this, I mean, over here it'll be pi over 2. Over here it'll be pi. It'll be 2 pi. So it'll be a spiral that goes out. That's what we get. How about r equals to sine theta? Well, this is sine of 1 theta, right? So what's that?
One pedal.
Huh? Rows with 1 petal, right? And if you actually draw this shape, this is what you get. You get this. You actually get a circle. It's rows with 1 petal. Circle is like rows with 1 petal. That's what you get. Now, you could draw this by making a table, but this is interesting because somehow this is a rare case where you can actually convert to the rectangular coordinate system, and it can be drawn just from the rectangular system. Okay? So here's how you change from a rectangular polar coordinate equation to rectangular. So what you do is, every time you see sine, you try to multiply by r, because I know what r sine theta is. What's r sine theta? Remember the formula? X is, y is, x is r cosine theta. Y is r sine theta. Therefore, r squared is x squared plus y squared. If you square this, add them up, because cosine squared plus sine squared is 1, you get this. So just having these three is enough to convert the given polar coordinate equation into rectangular. And this is how you do it. Every time you see a sine, what do? You multiply by r. So what are you getting? If I multiply by r both sides, I get r squared equals to r sine theta. Okay. Now what is this again? This is y. And r squared is x squared plus y squared. Now at this point, you might not realize what this is, but if you move the y to the other side, put it like this, and do the completing the square trick. So let's see, what's the completing the square trick? You take half of the coefficient of the first order term, which is 1/2. You square that and you add it to both sides, right? So you add 1/2 squared, what's that? 1/4. So you add 1/4 both sides. What does this become? Okay. All right, so that's the equation of a circle with radius 1/2, center at 0, 1/2, positive 1/2. Yeah. So if I just follow that prescription, let's see what it says. Center is at 0, 1/2. So 0, 1/2 is right here. This is 0, 1/2. And I want a circle that has radius 1/2. So this length is actually the radius. We have this circle. So as I said over here, this actually produces a radius of radius 1/2 circle passing through 1, 0. It's actually a perfect circle. If you just drew tables and drew this, you wouldn't have known that it's a perfect circle. But once we change it to this, now we know that it's a perfect circle. And that kind of makes you understand a lot other ones. Like for example, if you're given r equals to say a cosine theta, what would this be? It'll still be a circle with radius. What will be the radius of this circle? 4. See, this had radius 1/2. So this must have radius 4. Okay? Now, if you plug in 0, what do you get? You get 8. Right? So I know that at 0 ray, it has to pass through this 8. And I know that it has to also pass through the origin. And since 8 is the maximum thing, and you know that it's a rose with 1 petal, I know that it must be this circle. So this way, you can draw a bunch of other ones. Like, for example, if I had a minus in front, what would it be? It would be opposite over there. So now you know how to make equations for circles that are touching the origin, either this way, that way, or that way, or that way. So you should be able to write down these equations because later on, when you try to integrate over the domain where it's a circle touching the origin, it's easy if you use these formulas.